Hello friends, welcome to the ninth technical lecture by NCTS. Today's subject is guidelines on methoding and foundry tool design, first time right. And we will be getting the details of the subject from Mr. Sanjay Khanolkar. Mr. Khanolkar and his Metalcraft Industries is a well-known name in foundry toolings. He has an experience of more than a decade each in Tata Motors and Kirloskar Ferris Industries Limited. His visits to pattern shops in Europe, United States, and Japan have enriched his knowledge, and he has worked on toolings for almost all the tractor manufacturers in India. We will definitely benefit from his 35 years of experience gained while working in industry designing and manufacturing toolings, where the percentage of first time right is very high. I request Mr. Khanolkar to start his presentation. Thank you.
Good afternoon, friends. Let us start. This is my second lecture, so there would be a first 5 minutes. Possibly, there will be repetition of what I said earlier, just for the sake of who have not, for those who have not attended the first lecture. Now we are talking about tooling design, first time right. Today, everybody's patience has become so thin that the moment you get the order, the customer wants the casting, and that too with all possible deliverables, that is in the fastest possible time, best possible quality, and least cost. How do we achieve this? We can achieve this only if we think before we act. What are the challenges involved in this? Everybody knows universal deliverables are quality, time, and cost. I tell in our company, in interdepartmental also, every department has to take into account that whatever he delivers to his next processing agency, whether it is quality, whether it is delivered in time, and at what cost. Now, same applies to foundry tooling also. If we look at the customers' demands on the castings today, they want least possible weight for a given geometry, of course, minimum possible machining allowance, excellent surface finish, prompt response to modifications, less rejections or no rejection, cost of course less. Now, when we talk about quality, time, and cost, there were days when we were in a tremendous growth phase and everybody wanted everything yesterday or today. So time was the main thing everybody was following up, and quality used to take a little, I would say, the second seat, and the cost was not a major consideration in those days, earlier days. Today, all three deliverables are needed simultaneously, which makes it more important to do everything right for the first time. What should be our response when the customer wants something, or customer management, individuals, the organization want something right for the first time? Our response should be understand the customer's needs. Now, customers spell out their requirements through their drawings, through their dimensional or volumetric requirements, through their 3D models, through various documents, through various standards drafted by such companies. So to understand, many times I've seen people making pattern halfway through and they receive some standard document drafted by a big American or European company, and then everybody starts understanding or trying to understand what that document means. So it's very important that understand customers' needs before we really start to work. It's also more important to understand our own limitations. There's no point in having dreams of reaching a moon and even before we start using automobiles. Resist unreasonable demands. The drawings and customers can ask for anything, but foundry has to really understand, really assess what is possible at their end what is possible at any foundry's end, and then insist on removing the unreasonable demands. In this context, I would like to mention something about the international standards, or what various different international or multinational companies draft as their acceptance standards. They are all generally based on ISO 100 are supposed to fall within CTA to CT10 grade of casting tolerances. Now, if the customer demands something beyond this, one, either you can resist it or really understand and plan to deliver that kind of tolerance. Once the inputs are decided, once our own limitations are understood, then we all should put our mind and efforts to achieve the demands, provided they are mutually accepted. How to start? How do we start actually? Under so-called delivery pressures, thinking is something which generally takes backseat. कैसा भी करके चालू करो, material order करो. This is generally our tendency when we want to meet the urgency or the demands or time constraints, but generally that leads to delays. So thinking generally takes backseat under so-called delivery pressures, which should not happen. The second and most important thing is thinking does not cost. If all concerned people sit together, debate, discuss, and come to a positive conclusion, this doesn't cost. But doing something without really thinking about it definitely cost. In tooling or in engineering, particularly in tooling engineering, I call sixth sense is very important. And this sixth sense is nothing but evolved and goal directed common sense. Have full faith in planning and then plan everything to the last detail. Before we go to the theoretical part of my presentation, let me give you a small piece of advice for faster and better tooling development before we start on to the discussions on design of mold scheme. Mold scheme, if properly designed, will ensure in most of the cases you deliver the right product right the first time. Few years ago, we had a wonderful system called family doctors in our country. Family doctor used to be a senior doctor who knew every patient and his health history. He used to be aware of response of his patients to various medications and knew exactly what medicine will work for his patient. Medicines also used to be simple and time tested. Very rarely, he used to refer to his patients to a specialist. Today, there is a totally different scenario. Family doctor concept is gone. There are specialists for everything who need so many investigations to be carried out on the patient before the medicine is prescribed. In today's high-tech world, somewhere the concept of looking at the patient as a human being has slowly started taking a backseat. Something similar is happening in our foundry field. There are CAD experts, there are excellent 3D modelers, there are very good metallurgists, very good machinists, state-of-the-art CNC machines. But in my opinion, somewhere a family physician is missing who exactly knows what is good for his customer and for the foundry. Foundries in the advanced world, whatever I have seen, whatever number of foundries I have visited, have a very long relationship. In most of the cases, this relationship is continued over generations with their pattern makers. Something similar to a family doctor. In Indian context, unfortunately, this is not the case. This should change in the interest of both foundry as well as toolmaker. In the days of minimum 3 quotations and lowest wins, what suffers is the technical content. One more issue that I would like to stress here is the frequent modifications done on the pattern equipment. Every process, irrespective of the process control efficiency, is a variable in foundry. What is not a variable in foundry is the pattern equipment. Rejection percentage of a particular casting suddenly shoots up. Pattern is same over the years, but in the attempt to reduce the rejection, what gets modified is the pattern. In my opinion, before changing anything on the tooling, exact cause-effect analysis is a must. Finally, an ideal pattern development process which I would like to suggest is as below. So, as I mentioned briefly in my last lecture, the process or the number of steps should be like scope finalization, where we understand our own limitations, we understand customers' requirements, and then decide about the scope, what will be delivered and how. Then starts the design of mold scheme. Once it is over, 3D modeling, of course, is now a much easier task as compared to what we used to do in earlier days. Then design of actual core boxes, fixtures, patterns. At this, the next point is approval and discussions with user departments in Foundry. I would say that this is the most important point because this brings everybody on board. If all such designs are discussed with users or at least user department heads, then the reservations, if any, are brought forward right in the beginning, and it's much easier to make the tooling acceptable or liked by the user departments. Then raw material procurement, standard for procurement, pre-machining, CNC machining, assembly and inspection. Let us talk about scope finalization. This is a very important activity, but is generally not given its due importance in the beginning. Foundry purchase, sometimes end customers purchaser, development department in Foundry. In many cases, entire cross-functional team in Foundry are involved in this activity. Unfortunately, my observation is not at the same time, but at different times. Maybe there are too many cooks. Many times the recipe is spoiled. This leads to changes in the list of tooling needed, which leads to delays and cost escalations. Pressures of deadlines affects the quality also. So we have to take into account all these issues and then proceed. So first is make a list of tooling, correct definition of tool material, number of cavities, how many we would like to produce from our mold, what combination of cores in the core boxes. While deciding this, one has to take into account core flow in the core shop. If there are any assembly cores, then assembly cores should be produced nearby to the main core so that getting it there and testing it is much easier. Availability of core shooter and their capacity. Review of spatial costing tolerances and spatial gauging needed to achieve them. Small effort in the beginning to decide exact scope of tooling will lead to macro benefits in the overall tool life cycle. It must involve all concerned, including production departments in the beginning only. Once the scope is finalized, rest of the tool design can proceed without much surprises and delays. Once this document is finalized, it can be given to any tool maker or a machinist or a machining expert, where Foundry's active interaction may not be necessary. Now let us talk about mold scheme in detail. Mold scheme is a document which outlines how a casting is processed in Foundry. It also acts as a starting point in tooling development cycle. It is a bridge between Foundry and pattern maker. Objective of mold scheme, in simple words, is to produce a good casting in most economic way. Mold scheme designer requires thorough knowledge of practices followed in foundry for which the tooling is to be manufactured. It also means that a good mold scheme for foundry A may not be as good for foundry B. So there's no point in copying what somebody else has done or taking somebody else's tooling and trying to produce the casting in a different foundry. If a mold scheme designs, if at a mold scheme design stage, all areas related to casting making are properly addressed, it saves a lot of trial and error type of rework at a later stage. All molds As mold scheme is also a form of tooling, all basic principles applicable to any good tooling apply to mold scheme in addition to foundry specific considerations. Most of the activities in engineering industries, such as machining or assembly, involve much less variables as compared to variables involved in foundry. Considerations that should go into design of a mold scheme can be classified into following groups. Many big companies have their own standards, and these standards are generally derived from or derivatives of ISO 8062, which serves as a guide to supply and acceptance norms of the casting. The tolerance achievable on a dimension is a function of foundry process and that dimension itself. A smaller dimension will have much less tolerance compared to a large dimension. A casting made in hand molding type of setup will have different standard of casting acceptance as compared to high pressure molding line. Common understanding and proper interpretation of these standards is very important, and it should be arrived at in the beginning. Here, there has to be insistence from mold scheme designer on the purchase department that acceptance standards of the customer along with the customer's drawing should be made available. In fact, I would suggest that before accepting any order from any customer, these standards must be thoroughly understood and studied. If demand from the customer exceeds tolerances achievable mentioned in the standards, additional in-process checks might be needed to control the normal process variation. These checks may be in form of additional core assembly fixtures, templates, gauges to check particular dimension, and special care in fettling and additional casting checking fixtures. Casting weight is a direct function of casting dimensions, and hence tolerance on casting dimensions will reflect on casting weight also. In order to avoid rework on pattern equipment, acceptance norms for casting should be clearly defined with customer in the beginning itself. Sample casting is a great information source, and it must be referred to before starting mold scheme design. All possible attempts should be made to get the sample casting if it is available, and as it is an important source of information. Sample casting in most of the cases gives vital clues which help in taking right decision for the first time. However, one should not also get over influenced by the sample casting and must use observations made on sample casting in relation to the foundry under consideration. What to look for in sample casting? My experience of almost 40 years says that the sample castings generally are demanded, but they never arrive in time. They arrive after half the mold scheme methoding design is over, and then translating inputs received from sample casting, translating them into tooling or methoding becomes a very time consuming and difficult task. What to look for in a sample casting? Any additional features on the casting which are not there on the drawing. This has happened in my experience even with very advanced multinational companies where drawing shows something, 3D model is different, and the actual casting what is being used or what being produced is different. Many times foundries as well as customer modifies the pattern equipment to suit their requirement, which does not get updated in the drawing. If all such differences are pointed out right in the beginning, it saves a lot of development time as these changes are anyway required. It is important that such changes are brought to the notice of the customer and updated on the drawing. Somebody has to do it, so people have not done in earlier days or before. It's better that when we start our methoding design, we get it done. What sample casting tells us? If it is unmachined, so I suggest that whenever you ask for a sample casting, please get unmachined and preferably unfettled casting. It gives a lot of information such as parting line of patterns and core boxes, use of loose pieces in core boxes. Loose piece in core box is a pain. Even the core box is automatically operated or uh, operated or used on a most advanced core shooter. So whether loose piece is, although the drawing calls for a loose piece in a particular area, actual sample casting, you will see that there has been a modification and the loose piece has been eliminated. So this such information is very easily available if we look at the sample casting, preferably unfettled. Removal of undercuts by addition, removal of material. The small undercuts is a huge pain to achieve in foundry, and we struggle, put slides, put separate cores just to get that profile. And later on, after a few years, somebody realizes that some other supplier has simply added some material there, and he has made his tooling simpler, his life simpler, and his casting simpler. So removal of undercuts by addition or removal of material is something that we look forward to in a sample casting. Location of ingates and flow offs. If somebody has invented a wheel, there's no point in reinventing it unless the wheel is not running properly. So if you look at the unfettled casting, we get the locations of ingates and flow offs, locations of paints. Then comes scope and rack selection. The casting gives you a clear-cut indication that which scope has been considered earlier, and then we can debate whether we should retain that or we should go for a different system. Extra material in features such as general wall, bosses, various. Extra material is something which is like an insurance policy, although it adds to certain amount of weight, the pattern equipment to a very serious extent. If you have sample casting, if you identify and define the extra material which you have observed on the sample casting, same can be updated or communicated to the customer and regularized. Various logos and identification marks, their location, use of chills, chaplets, actual dimensions achieved against tolerated dimensions on the drawing. Drawing says something, but actual dimension is different. Such experiences after the casting is made need not be there. You can always compare and get some idea before we make the tooling. Casting weight is a very important idea that we get if we get a sample casting and weight, and what machining allowances are actually being used by the customer's machining setup. These observations are only guidelines. I don't expect people go and fight with the customer and say that your sample casting is like this, so my casting also is going to be like that. But this is a guideline, and based on which, whether we can improve, whether we cannot improve on that, or if we will be happy if we achieve that. So this judgment has to be made by the mold scheme designer, and current requirements of the customer are always more important. But if they are unachievable, it's always better to debate, discuss on those requirements beforehand, and you have a sample casting as a witness. Attempts should be made to simplify the casting making by suggesting small profile modifications. This is possible if functional requirements of customer are properly understood. These small changes, if suggested initially, if they eliminate few slides, couple of cores, then it's a huge saving and great simplification of the entire casting making process. Now let us talk about machining allowances. In today's competitive market, we found the foundry is always pressed for casting with minimum machining allowances and minimum finished part weight. While deciding machining allowances, customers' concurrence at the starting of model making is always advisable, as it reduces possibilities of rework on the equipment after samples are submitted. Draft angles play a major role in increasing machining allowances. is that machining allowance is being formed by a draw phase. In order to keep machining allowance within acceptable limits, draft angle needs to be reduced, particularly on the faces which are more in height. As chances of mold breakage also increases with deep drawn faces with low draft angles, due consideration should be given to mold making also. Because many times it happens, customer is insisting on half a degree draft angle just to reduce the machining allowance, and then tool maker ends up with giving that half degree, and then while making a mold, you either get a porous mold or mold not compacted very properly, and you have sand fusion and you end up with having more machining allowance or more problems during machining. However, without customer's prior knowledge, machining allowance should not exceed 6 mm in any case. So on the other side, I'm cautioning, if 1 degree draft angle is better than half degree, there's no point in simply giving 1 degree without really understanding what effects it is going to have on the casting. In many situations, a face is formed by more than one element. So a machine face is formed half by the core surface and half by the pattern surface. Now, these angles are generally reversed. So you have a crisscrossing kind of surface on the flange face or a face where there is a core print nearby. This leads to uneven surface because of reverse draft angles of different elements. In such cases, machining allowance should be maintained such that the step appearing of the casting is distributed around a mean value. Like for example, if the reverse drafts are inevitable, if you start from one point and there's going to be a difference of 4 mm, instead we can maintain the mean machining allowance at the center and then have it plus minus 2 millimeters. Initial reference points for machining. This all what I'm talking about is what when one should look at when you get a sample casting. These points should be identified and highlighted on the component drawing. These points, which are generally 3-to-1 type, that is a modern way of machining the casting, should not have any extra material and have minimum possible draft angle. Extra material on the casting. Although extra material or extra wall thickness means extra casting weight and hence loss to the foundry and in turn to the customer, it helps foundry to counter process variation. General wall thickness of the casting should be aimed at the mean of the upper tolerance. If wall thickness specified on the drawing is 6 plus 1.2 minus 0.5 as an example, then pattern equipment should be aimed at 6.6 millimeters. Added 0.6 acts as a safety factor against process variation. If casting drawing does not indicate any tolerance, then 0.5 millimeter extra material is to be considered from pattern side. In addition to general wall thickness, extra material is desired in following areas. A big exercise we conducted with Mahindra designers and with people in Tata Motors, where what should be the diameters of the bosses in cores as well as on pattern, cylindrical bosses or spherical bosses. Then we arrived at following guidelines. For tapped holes up to M8, minimum diameter of boss should be 2.5 times the nominal diameter on the of the tapping. For holes M10 and above, it should be 2 times the nominal dia. If this situation already exists in the drawing, then provide only 0.5 millimeter extra material provided on radius. So diameter of the boss will be 1 millimeter plus. All other bosses in the casting should be increased on diameter by 2 mm and by 1 mm in depthwise direction. All oil galleries in cylinder blocks and heads should be increased by 1.5 millimeters on radius. These are the lessons learned through very costly lessons, because the oil holes are generally deep oil holes are drilled by gun drilling or deep hole drilling, and there is always a wandering of drill. So although on drawing it is mentioned as a straight line, drill wanders inside the casting material. So you need that 1.5 millimeters as safety allowance. For water jacketed blocks, barrels of water jacket core should be bigger by 1 millimeter. All deck walls in cylinder blocks and cylinder heads should be more than 1 millimeter. After all these allowances are finalized, they should be updated on the component drawing. Tappet openings are often reworked for less wall around tappet holes. In order to take care of this extra material of 1.5 mm should be provided per phase. At this point, I would like to mention an experience we had with Nissan Diesel, that was Volvo Group company, and Volvo's BS6 engine was designed by those people. When we first went there to develop their engine blocks, nobody was ready to agree that over and above casting drawing or a 3D model given for casting or the product, some material is added by the tool maker. Nobody was ready to accept or regularize that. We had a meeting with their foundry in Japan, and when we listed all these points which I have listed now, they uh, virtually agreed for every point that we mentioned here. I have mentioned here. So these are the practices followed world over. But if we are not aware of these practices, and if we are trying to do something, then instead of doing right for the first time, it becomes something which definitely needs some corrections. So whatever the additional materials that I talked about in my previous slide, this practice is generally accepted by customers in tractor and truck industry. But one has to be more careful while dealing with castings for car. In all such cases where the requirement is very critical about casting weight and machining allowances, extra material policy should be finalized and documented in consultation with customers and foundry. Customer drawing, thus modified, should then be converted into reproducible format such as CAD data or on a tracing sheet. A copy of this drawing should be sent to foundry highlighting the changes made. Extra material at this I'm mentioning if toolmaker is right. If foundry is doing it, they have this information already. Extra material added on pattern and core or core box to take care of process variations is not something new, and all leading foundries in Europe, Japan, as well as USA have this practice. Only thing is nobody will tell openly that they are doing it. This extent of addition depends upon the level of automation, process control in respective foundries. We must accept this practice and follow it right in the beginning. It will avoid a lot of corrections needed later on the tooling. Let us talk about casting identification. This is something even customers, designers forget to mention on the drawing, and then somebody looks at the sample casting and they realize that there is ISO, there are so many standards, and then traceability and identification are important considerations. And then everybody starts running after. Then customers have some specific logos. Those logos don't have drawings. They need to have the 3D models of those logos. So all this has to be identified and the information should be collected before we start. Every casting requires casting identification from casting traceability point of view. This includes two types of identifications. Identification marks indicated by the customer, they are as follows: customer drawing or casting number, customer's logo and emblem, pouring date of the casting, code numbers allocated to the foundries. Generally, this information is shown on the component drawing, but many times it calls for some standard drawing which is made by the customer. If customer has not given these drawings, then a follow-up is required with the customer. This saves a lot of running around when the pattern is ready. If location of these identifications is not clearly indicated on the drawing, then a clarification is to be obtained from the customer, as in many cases, these positions are important from visibility point of view after the casting is assembled onto the vehicle. Identifications desired by foundry. In addition to the identifications demanded by the customer, foundry needs for their own internal traceability, set number of the pattern equipment, the cavity numbers of the, if there are multi-cavity patterns. These identifications help in rejection analysis as well as keeping track of subsequent modifications made on the pattern equipment. Many times, core inventories are available in shop, which can cause mix-up of cores before modification and cores after modification unless proper identification system is available. Then let us talk about general consideration. These are important considerations specific to the foundry under consideration, which may vary from foundry to foundry. One is deliberate fin. Fin is desired on the equipment where more than one element, such as mold or pour, or two different pores, or two pores and mold meet. There is generally a sharp meeting of two or three sharp corners of different elements, particularly in the casting area. Fin helps in avoiding sand inclusion at sharp junctions in this casting, which creates hard spots in the casting, which because of heat spot and then sand fusion at that particular location, resulting into hard spots, which affects cutting tool life in machine shop. It also helps reducing sand drop while core placing and core box closing. A care should be taken in providing fin as it reduces core resting butting area. So somebody has said that core fin is good and there is small print touching another core, and if we provide a generous fin, then core resting gets reduced. So that also has to be well balanced. To avoid confusion, fin should be provided as locations given below. If there are multiple cores like cylinder blocks, if it's six cylinder block, there will be 8 cores, front and rear end, and 6 cores. So while giving fins, we call it Nissan fin, some people call it Nissan fin also. These fins should be, a foundry should decide their own practice and say, at mold to mold interface, we will provide fin in drag only. Because if you end up providing fin both the elements, you have double the thickness of fin and then it is difficult to settle. At mold to core interface, around the casting profile in pattern. Core to core interface in left side or bottom side of the core. You can decide any of these guidelines, but these guidelines must be followed everywhere. Then there is sand cord. Sand collecting cavity is provided on drag mold to collect the loose sand which falls while core setting in the mold because of rubbing of core with the mold walls. This cavity collects sand which otherwise will fall on resting area of the core, resulting into high setting of the core. This is called as sand cord of the pattern, which is generally 5 mm wide and 2.5 mm in height. Although sand cord helps in core setting, it is likely to connect the metal with a hollow outs in the core, resulting into mold leakage. In order to avoid this sand cord should start from 15 millimeters away from the casting. So there are no direct linkages or leakages that can happen from the casting metal to the hollow outs in the cores. Crush groove. Clearances are provided in the pattern equipment to take care of process variations. Sometimes the clearance is not enough for metal to leak through the mold. If the clearance is enough for metal to leak through the mold, in the mold, leakage takes place. If clearance cannot be reduced further, then a crush groove of 2 mm into 90-degree V-shaped crush groove is provided on print area near hollowouts in pattern so that the green sand is crushed there and it seals the passage. Generally, it is provided in cope pattern. Contraction allowance, this is something we can spend little more time on. Contraction allowance is primarily a function of solid to solid contraction in casting after the metal solidifies till it reaches the room temperature. Most of the foundries work with 1% contraction for gray iron. Contraction also depends on following factors: rigidity of the mold and mold wall movement, types of cores used, and the nature of cores used, hollow or solid, shell or cold. These factors influence the contraction because of resistance offered by them to the expansion during the graphitic separation phase and then to the solid contraction. These factors increase or decrease the contraction allowance depending upon the mold rigidity and the strength of the cores. My experience for gray cast tends to suggest 0.8% contraction allowance for high pressure molding line and solid cold box core box combination. However, for cylinder heads, 1.2% or little higher contraction allowance is needed. Uh, Whatever I'm saying might look a little too theoretical for somebody, but for those who have worked in methoding section or who have been who all are being have been doing methoding job, they will understand better. Core prints. Let us talk about core prints. Core prints are the connection between core and mold. So that is where the product designer allows foundry engineer to rest his cores into the mold. Each opening in the casting can be used as a core print. Openings in the castings are provided for following reasons by the product designer. Functional requirement of the casting. The casting needs that opening. Then access for sand removal during fettling. And then core resting and location in the mold. Openings in the casting can serve one or more functions together. These openings are important considerations in mold scheme design. These openings open into prints. Prints should be of geometric nature as far as possible. Prints locate and hold the core in position. There should be no overlocation of core other than usual 3-1 or equivalent. If too many prints are there and too much tolerance, tolerance is provided without much clearance in the pattern and core, it can lead to sand crush and improper positioning of core. So usual 3-1 or equivalent core location technique should be used. Print should be such that they locate the core into the mold with proper resting area. But too many locations or locks can lead to mold crush. In cases of redundant core prints, clearances should be naturally increased. Prints should be such that they do not break during core handling or core placing. So they should be rigid. For example, in crankcase cores, instead of male locating prints, female locating prints are preferred, as they are protected and they do not break. This is particularly more important in fixture location prints. Prints should be visible while placing the core, as prints which are not visible can create problems in core setting. Many times some cores are pasted on another core. In such cases, arresting all degrees of freedom is not possible. It is important to hold the pasted core in position till the gum is set. Excess core wash always creates problems in core position. Hence, proper wash collecting groove or a cavity to be provided in receiving cores. Storage position of core after washing should be taken into account while providing wash collecting grooves. Whenever core to core gumming is required, proper gum collecting grooves also need to be provided. Then let us talk about the print clearances. Clearances are decided based on following considerations. One, reliability of core and mold making. Only because we want very accurate casting to be produced, if we reduce print clearances and if our core making is not reliable, if the mold making is not proper, then there is no point in tightening the clearances without really understanding this. Core placing accuracy, manual or with fixture. If it is manual core placing, then clearances should be little higher. With fixture, you can go for little tighter clearances. Function of the core print. Whether core print has been provided to locate the core or just for sand, removing the sand, or it is functional requirement of the casting will dictate what kind of clearances should be provided. Then size of the pattern, of course, will decide. If it is a 3 meter long casting, naturally we won't expect 0.5 millimeter of clearance on the sides. and then the accuracy required on the casting. For mold schemes or high pressure molding and machine mounted core boxes, following guidelines are to be used. Clearances should not be tight unless they are locating the core. For core to mold clearances, for drag mold, 0.2 mm in core resting direction, 0.5 mm in sidewise direction. Cope mold, 0.8 mm in sidewise direction and 0.5 mm in heightwise direction. For core to core lock prints, 0.8 mm all around and 2 mm in depthwise direction if core to core butting is on some other face. For IBB and water jacket cores in cylinder blocks and for base core and water jacket core in cylinder heads, 0.8 mm all over except 3 prints which locate the water jacket in X and Y axis where clearance should be 0.5 mm. When I say all this, a proper consideration of washing practices, how the cores are printed, whether they are printed after assembly, whether printed before assembly and then pasted, will have a implication or relation with the clearance that is to be provided. In resting areas of water jacket cores, it is preferred that a grinding operation is introduced with 0.2 mm clearance. At base, unique plane can pass through 3 points. Other prints should be provided with 2 mm clearance from base core. Circular print mold to core 0.3 mm in drag mold all around and 0.5 mm in coke mold all around. In cases such as crankcases, butting faces of cores should have 0.2 mm per side clearance where many cores are placed in line, just to eliminate the cumulative error. One more important consideration in deciding the clearance is the core wash. If the core wash is expected to be there on core locating prints, which is not desired as it reduces core permeability and tends to increase casting defects, then clearance should be increased by corresponding amount, which is normally 0.2 mm. All attempts should be made in foundry to keep wash thickness at the designated value, designed value, by controlling the washing process parameters. Care should also be taken to ensure that the vent holes do not get blocked by the print. Draft angles. Higher draft angles always help in core as well as mold stripping. As long as there is no effect on casting and core resting, generous draft angles are desired. In drag mold, 5-degree draft angle on all sides is desired, whereas in cope it should be 10 degree. In self course, generally 5-degree draft is desired, but if this is a casting profile, then it has a direct effect on casting dimensions and hence maximum permissible draft by the customer is to be provided. If the self core is deep, depth to width ratio is more than 1, draft angle allowed is less, and if the draft angle allowed is less than 3, then possibility of using a ram up core, you can put a separate core there and mold it along with the put it on the pattern and mold it along with the while steeping of the mold. Ram-up core is a small core placed on the pattern before molding and becomes a part of mold as the mold is stripped off from the pattern. In course, many times round or kidney-shaped openings in castings are converted into prints. In such cases, double draft angle is required. By double draft angle, I mean it is generally 1 degree in casting area, but 1 degree if we continue, it makes the core shop's life extremely miserable because small prints, kidney shaped, and with 1 degree draft angle, it is extremely difficult to make, whether it is cold or shell. So in casting area, it is 1 degree and 3 to 5 degree in print area. On faces formed by pattern which get fully machined, draft angle is always critical as it leads to excessive machining allowance, thereby increasing machining cost. In such cases, maximum half-degree draft angle is accepted by the customer. If mold making is difficult and customer is not likely to accept higher draft angles and hence higher machining allowance, then introduction of a core in that area should be explored. What is more important is that this issue should not be discussed with the customer after the pattern is made. So it has to be settled before the pattern is made. Core resting in mold. Core resting in mold should be sufficient to take weight of the core. Compressive strength of the mold for high pressure mold should be considered as 2 kg per centimeter square. Once the metal is poured, buoyancy force acts on the core, and because of the difference in densities of core and metal, upward force is around 4 times of the core weight acts on the mold. So we generally give attention to the resting of the core in drag, but what becomes more important of the metal has come in is the resting area available in coke. So core print in coke should bear this thrust and should be designed accordingly. While deciding core print sizes, it should always be kept in mind that bigger core print means extra core cost, and hence print should not be unnecessarily big. Many times excessive prints restrict number of castings also, which can be accommodated in a box. But then it is always a fight between quality and quantity, where golden mean is always desired. Many times prints are not well distributed in the casting, and sometimes they are insufficient. In such cases, core needs to be supported using chaplets. Chaplets are of different types, and they are classified based on sizes as per casting walls, 8 mm, 6 mm, 10 mm, based on shapes for avoiding mix-up in foundry. So it's a good idea to have 6 mm chaplet. If it is round, then 8 mm chaplet can be rectangular, so that by mistake, wrong chaplets will not be used. And based on the load, heavy duty chaplets, normal chaplets, and so on. Chaplets, whenever used, should be selected from standard chaplets. No chaplets are decided. Number of chaplets are decided considering following factors. Standard sizes, of course, is the main consideration. Then weight of the core, location of chaplets, metal buoyancy force, time required for facing the chaplets, and available core resting. For deciding number of chaplets, following method to be used. Unsupported load of the core is equal to core buoyancy minus core print support. Core buoyancy is 4 times the core weight. Print support is print area into strength of mold, that is 2 kg per mm square. So 4 into core weight should be less than or equal to 2 times print area plus total chaplet area. Chaplet sheets are provided on rack pattern for mold to core chaplets, and in cope half of core box for chaplets between core and core. Chaplet sheet should be 4 mm bigger in diameter, and height of chaplet sheet should be decided such as to enable use of standard chaplet. So if your casting wall is 9.5 and 10 mm or 11 mm chaplet is available, accordingly a depression can be made in core so that standard chaplet can be used. Location of chaplet should take into account problems related to chaplets in casting, such as leakage because of non-fusion of chaplet material with the base material. Chaplet between casting walls which have two different fluids on either side in the ultimate final casting should be avoided. For example, if there is a air passage and if there is a water passage or oil passage, there should, as far as possible, we should avoid chaplets between two such passages, so that the chaplets are not fused properly. The streams, air doesn't leak into water or water doesn't leak into air. Cope and drag selection. How do we select cope and drag? This is an extremely important consideration and needs study of casting drawing from all possible angles. Most of the time, geometry of the casting itself decides the cope drag selection because of core openings. In such cases, selection of cope drag is much easier because there's the only way how you can select cope and drag, because the prints are given that way. Core placement is possible only if cope drag is selected in a particular way. If core prints allow cope and drag in either direction, then other considerations become more important. Machining reference points in drag. Many customers machine their castings by taking direct reference from the as-cast surfaces on the casting. If these reference points are coming from pattern side, it is desirable to have them in drag. Generally, surfaces produced by drag from drag are smooth and without casting defects. In cope, there is also a possibility of a vent pin or a flow up coming in or near the reference points, which is likely to have fettling variations besides other defects. Heavier shell cores in drag. Shell cores, whenever used, particularly in case of cylinder blocks, you will observe this. There are oil passages, there are water passages. So heavier shell cores, wherever they are there, should go preferably in drag. Shell cores, whenever used, lead to more gas-related defects in the casting than cold box cores. Hence, treatment of shell cores is important. Normally, cores are drilled and gases are vented out of the mold through the passages provided. As metal also can enter in those passages, they can get blocked. This leads to casting defects. Castings are less sensitive to gas-related defects if heavier shell cores are placed in drag. Whenever shell cores are on both sides, smaller shell cores should be placed in coke. Number of castings per mold. Attempt should be always made to maximize yield per mold, which should be more than 150 kg. I am just giving a rough guideline for a 1200 by 900 box size. However, liquid metal to sand weight ratio should not be less than 1:4. A multi-cavity layout, minimum mold wall between becomes an important consideration. Normally, following considerations are made in designing mold wall for mold to mold making and in mold leakage point of view. Cavity to metal cavity should be 50 mm. If runner bar is passing in between, then at least 35 mm should be left between casting and runner bar. If cavity is deep and distance between cavity is limited, then runner bar can be split in half cope, half drag. So you reduce the height of the runner, and maybe that helps in bringing the casting little closer. Age of the box to casting minimum 55 millimeters. Age of the box to core print minimum 40 millimeters. Wall is design. All borderline cases, like suppose we deviate this guideline by 10 millimeters, we are able to accommodate more number of cavities. Then they need to be discussed with foundry, molding, and related departments. For a given box size, position of screw is also important, as the screw cutting machine can approach only specific area. Twin block type layouts increases number of cavities per box, but it has problems associated with core storage and core handling, as on top as well as on bottom side of core there is casting profile. These issues need to be discussed with foundry before taking a decision about the print sizes. Maximum number of cores per mold. Although number of cores in a mold is primarily decided by casting drawing, while doing multi-cavity layouts, particularly, number of cores should not exceed 12, as it will result in core setting delays. As an alternative, special core setting aids or introducing core subassemblies and should be thought of. Time available for core setting in final core setting fixture is around 40 seconds maximum for a molding line with 70 molds per hour kind of speed. Additional bottom up of FCSF can reduce core setting delays, so we can split the operation. Two assemblies are done parallelly, but it should be again discussed with the concerned foundry setup. More than one castings in one layout. This was a theoretical question asked to me by somebody. It is desired that all castings made in one box should be of same time. But if coreless castings of same metal are available and space is also available, they can be accommodated in the same mold. So we can produce free castings. Productivity of core box is important. So our the mold scheme design also should think of the plan size of the core box also. Suppose by reducing a print by 10 millimeters, if I am able to make a 2-cavity core box by thereby increasing my core shooter productivity by more than 100%, it should be attempted. Productivity of core box is important, and available core box should be fully utilized to produce maximum number of cores per core cycle. Core box layout is also should take into account the core box changes involved, as the core box changeover time is a non-productive time. All attempts should be made to reduce number of core boxes per casting. So that reduces the number of castings required to produce a particular casting. Another consideration in deciding the core box configuration is the cycle matching of core shooters. It is always preferred that all core boxes required to produce a particular casting require same number of core cycles. Many times, undercuts in cores require loose pieces in core boxes, and these loose pieces increase dry cycle time of the core making and reduce the number of cores in one core box. They lead to core making related problems also. Hence, it is always desirable to eliminate loose pieces either by getting the casting profile modified by the customer or by introducing a pasted core. If by introducing a pasted core, productivity is doubled, instead of one, two cores can be accommodated, then it is always the first preference. If loose piece can be eliminated using a pasted core, but without increasing number of cavities, then it should be discussed with the foundry. Pasted cores such introduced should be accommodated in the same core box without increasing number of core boxes. Aids provided for casting making should be simple but effective. Too much mechanization is difficult to maintain in foundry environment. So it's not a rocket science, and that kind of designs don't work in foundry, and hence it should be avoided. Core making aids are as follows. Core checking templates. In order to avoid core rejection and casting rejection, core checking templates are required. They are in-process gauges and should be rigorously followed. Templates should not check all but only important features. What can vary in a core box when the cores are produced is the thickness of cores across the parting line, which are likely to vary during core making. If all cores are made on core shooting machines, dimensional variations are not expected to a large extent. However, cores such as sport cores of cylinder heads are very critical, and templates such as core to core check, such as cores, templates for such cores to check oversized cores across parting line are extremely essential. Cores made on transfer core shooter machines where core box is not clamped during transportation to curing station, particularly if the core box is has got machine operated loose pieces, they need a detailed review of such templates for critical dimensions. Core holding aids, particularly if the small cores are to be pasted on main core and stored against gravity till the gum is set, some clamp or a rubber band like aid needs to be provided. Templates to ensure correct positioning of pasted cores are also needed. Core drilling aids. Initially, drill bushes for drilling of tie rod holes in water jacket cores or venting holes in any other cores should be supplied. But if the number of castings required is large, the pneumatically operated drilling fixtures should be provided in the second phase. Core grinding templates, cores where grinding allowance is provided to achieve critical dimensions such as deck walls in a cylinder head or cylinder block, should be provided with core grinding templates. Obviously, core will have to be provided with grinding allowance. Need for all such aids should be clearly indicated in the mold scheme. A requirement for multiple sets should also be discussed with the customers. Correlated parting line of course. Core should have parting line as simple as possible, because it has to also take into account the gas leakage and the sealing of rubber sealing and so many other issues. So it should be as simple as possible. It should be clearly represented in the mold scheme. So boundary designer should indicate what parting line he needs for the course and accordingly communicate it to the tool maker. Parting line of cores, if correctly represented in mold scheme, helps in providing matching drafts. So later on, no surprises, extra machining, excess machining, less machining, no machining. It also helps in reducing compound angles in the core boxes, which are difficult to make as well as measure. Those pieces are also correctly identified, which helps in deciding core box combinations. Sample casting should be referred to wherever possible for indications of such parting lines. Many times material addition because of draft angle becomes critical from casting, machining and fouling point of view. It is extremely difficult to change parting line orientation once the tool is made. Core resting. Resting faces of the cores in mold as well as on trolley, that is in storage, is important. Both should not be the same because the resting of the core in mold defines the quality of the casting or the dimensions of the casting. Whereas storage prints just help the core to keep the core properly stored without damaging the profile part of it. Both should not be the same. Trolley resting area should be such that core is stable on the face even during transportation on core trolleys. Cores are generally dip painted, so core storage should take into account dipping as well as accumulation of excess wash on important core faces. During intermediate storage, core should never rest on casting profile. As cores are normally dip painted and kept on trolley after dipping, prints are designed such that the excess core wash is drained off or collected in a wash collecting groove. Core location. Locating of cores is important for dimensional accuracy of the casting. Core location in final core setting fixture. All possible degrees of freedom should be arrested while locating the core in fixture. It is also important that core is not over arrested in the fixture. If cores are progressively assembled in bottom up, only one core per independent core package should be located in all directions. Other cores, if they are arrested by locator core, main core, and then they should be located only in other two directions. If cores are overlocated, it leads to core damage as well as incorrect positioning of the mold in the mold. Core location in mold should also have similar consideration. However, if core package is heavy around 100 kg, it takes the position dictated by the fixture. Mold cannot correct core package if it is wrongly placed by the fixture. Core handling. Core is a delicate object for handling. It needs proper designing consideration for providing core handling prints. Handling of core takes place in following locations: while core making, while core washing painting, then set making and assembly making, and on final core setting. Although best way to handle the cores is manually, like how the human infants are handled. Cores weighing more than 25 kg should not be handled manually. Tackles for all such big cores are needed. In order to get the correct idea of intermediate handling of cores, foundry should produce few sample castings, then design the tackles for heavier cores. Design should be finalized in consultation with the foundry. As core lifting points in fixture have an impact on casting accuracy, these core handling points should preferably be different from handling points for tackles or other locations. However, many times print sizes and hence core handling points are restricted. In such cases, fixture link design should give due consideration to this factor. Final core setting fixture core handling points should be preferably in cope. If this is not possible, then proper link reliefs should be provided in drag pattern. Core hollowing is again a disputed issue. Core weight is an important consideration in costing of the casting. Hollow cores weigh less and hence cost of sand and resin is less if cores are hollowed out. Wall thickness of around 22 mm is desired to prevent core from deformation under metal pressure. Proper rebbing in cores also is desired if hollowouts are big. Openings of such hollowouts should be plugged using plug cores. Plug core should be common as far as possible and should be made from same core box if possible. But if metal enters in these hollowouts, in spite of taking all precautions, then it offsets all the cost related calculations as the metal cost is lost. Metal is lost and leaked metal can lead to some casting defects. So study of tooling made so far indicates that it is beneficial to make core solid instead of hollowing them and then again plugging them. It also offers greater flexibility in getting design. Core fouling. Sometimes people experience this after the tooling is made. Many times the casting geometry dictates that core should be placed in a particular order. As one core falls with other core while lowering in the mold, in such cases, core splitting becomes necessary. So half core you place first, then other core, and then the remaining half part of the core. Alternatively, core is lowered first at a distance and then laterally moved to its required position. Extra clearance provided for lateral movement needs to be filled up by another wedge type core. If the cores are being placed by using a fixture, then a movable trolley can be introduced in the fixture to take care of this problem. Blow tips are required to blow the sand in the core cavity. Blow tip come as projections to the core and they need to be trimmed off to the core profile. This calls for extra manpower and needs care in matching with the core profile. Hence, blow tips are preferably provided in print area where machining with core prints can be avoided. If corresponding relief is provided either in pattern or in the receiving core. Special consideration for blocks and heads, those who are dealing in cylinder blocks and heads. Port cores and their positioning in the final casting is considered to be very critical for meeting emission norms of engines as it is insisted by the product designers. This calls for additional precautions in tooling as well as in foundry. All port cores have a tendency to high seating or getting lifted, and it is because of cumulative effect of following. Core was closing, parting line gap, excess wash, excess gum, buoyancy force of metal. This leads to casting rejection. Although these factors contribute to extent of 0.1 to 0.2 millimeter each, their cumulative effect could be as high as 0.7 millimeter. This is a very critical point and hence special core setting gauge to ensure that port core heights are as
So,
designed, they should be provided.
so slide change झाली नाहीये.
अरे सॉरी हां, दोन कॉम्प्युटरवर घेऊन बसलोय.
Yeah. Thank you.
Cylinder blocks. As cylinder block is a long train of many bore pores, cumulative effect of core growth affects the end dimensions of the casting. To take care of this problem, crankcase cores are made undersized by 0.2 millimeter per butting face. Mold-related draft angles in self cores. Greensand mold is delicate mold and hence it should have generous draft angles as far as possible. Draft angle is required by foundry, which leads to either extra weight or extra machining allowance on the casting, which is often objected by the customer. A golden mean is desired regarding draft angles after fully understanding the functional requirements of both. Cell cores are always difficult to mold, and 1 degree is inadequate to produce a good mold consistent. Hence, all cell cores where height to width ratio is more than 1 should have at least 3-degree draft angle on pattern. If functional requirements of the casting does not permit this, then introduction of a core becomes a necessity. Location of screw. As screw position is dependent on travel of screw cutting machine and travel of press pore, coordinates of screw should always lie in those prescribed limits. Parting line leakage. Mold wall towards edges should be sufficient to be able to produce good mold, to prevent the metal leakage from the cavity to outside the mold. Parting line leakage not only leads to casting rejection, but also leads to damage to the mold boxes. If the end wall is less than 80 millimeters sand to sand contact, then a crush groove of 3 millimeter by 90 degrees should be provided in this area to avoid leakage. Settling related consideration. Parting line selection. Wherever two elements of the mold scheme meet, a fin is produced. It can be controlled if clearances are controlled. In many situations where as-cast hole is produced by two elements, at the interface of them, a fin is produced. In these cases, care should be taken to part the profile such that it is easier to remove the fin and it has a better approach. If such fin is in the area which eventually gets machined, it need not be removed. Location and size of fin can have an influence on fettling productivity. Male-female prints produce fins which are easier to fettle. Horizontal fin, vertical fin. Openings in the casting are normally used to provide core prints. If the opening is of complicated shape, then print shape should be simplified as it is easier to manufacture as well as to measure. While simplifying these prints should be made bigger than opening as far as possible. This leads to a fin in horizontal direction that is normal to the casting, which can easily be chipped off. If the print is made smaller than the opening, then it leads to a fin in vertical direction, which is difficult to chip off, and the casting damage is likely to occur while doing. Thickness of the fin in this case is also more than there is a possibility of core rubbing with vertical mold wall. Chipping of horizontal fin at times leads to casting rejection because of crack on the casting during hammering of the fin. Fettling templates and gauges. Many times, customer requires a particular opening or a profile to qualify for a particular dimension. Fettling templates need to be provided in such cases as a reference to the fettler to work. In cases like water openings, sometimes castings are machined with some fixed references on the casting which should not get over fettled during fettling. As an alternative, extra material is kept on these pads, which is then ground off using a grinding division. Gating and venting system. Due consideration to gating and venting is required before finalizing the mold scheme. Position of ingots and their configuration influence casting rejection. Gas venting also plays an important role, which depends on print clearances and matching drafts. Guidelines for gating and venting are separately discussed, but as a general rule, it can be said that metal should enter the mold as smoothly as possible. That is called laminar flow. Air in the mold and gases generated during burning of the core resin should be adequately evacuated to avoid their entrapment with the metal. Metal velocity in the mold should not exceed around 80 centimeters per second. In-gate position should be selected such that there is even temperature distribution of liquid metal in the mold. Temperature variation in the cavity should be minimum possible. Metal should not enter gas or air passages, and gas should not enter the metal passages. They should be properly isolated. Avoid sharp bends in gating systems. Ensure that the metal stream does not hit the core directly. General idea of metal running should be finalized right in the beginning in order to avoid major changes in prints later on. Speed of post crush grooves largely depends on the path of metal. Confusion leading to dimension being considered at wrong location. Generally, if you refer to the 2D drawing, dimensions are placed in plan area, but that doesn't really specify whether that dimension is required at the top or the bottom. Toolmaker, as a matter of practice, it considers every dimension given in the top of the pattern and then adds draft just to add the material. So this confusion leading to dimension being considered at wrong location needs to be settled in the beginning. Adequate number of sections should always be drawn to give the required clarity. This, of course, applies more to the product designer. All information related to casting making should be given in the drawing on the mold scheme. So mold scheme should summarize what all thought process has gone into this design, as it is the document which starts many parallel tool making activities, and it is the drawing which is frequently referred to in foundry. This information is as follows: names and numbers of cores required, estimated weights of the cores, process to produce this cores, machines to produce this cores. Production aids if used. All attempts should be made to use these production aids, such as tie rod chaplets, foam filters, U clips, C clips from variety already in use. Only relevant notes indicating contraction along general radius, etc. Extra material, if desired, in the equipment should be shown on the mold scheme instead of giving only a general note. Drafting should be neat and clean. So these are general age-old guidelines which are being followed or have been followed by good people over the ages. Understanding of customers' initial machining operations is required as it has a large influence on the parting line. Overdraft selection, I discussed this earlier. So, and hence machine shop rejection. System of initial reference points has evolved over the years. This evolution can be classified into following stages. This is just to give an idea of those who have not seen the earlier machining practices. I have seen companies where averaging and then generating the initial machining reference manually. Generating machine references with fixed reference from. Second is generating machine references from fixed references from the cast surface, but done at the foundry end, that is averaging. Directly machining the casting using cast surfaces. Customers' machining setup can be at any of these stages depending on quality of available castings. As most of the customers have 3 to 4 casting suppliers of their major castings, it needs to be common for all of them. So there is no point in we suggesting something whereas 3 other suppliers are suggesting as per the old practice. First 3 stages require additional efforts for foundry so that casting is ready to be machined in the customer setup. But this also ensures that casting dimensionally qualifies the customer's needs if proper sighting fixtures are used. It also leaves some scope to the foundry to salvage the casting by adjusting the allowances. That is, I'm talking about averaging fixtures. In last category, customer directly machines the castings from the as-cast references. This system can work effectively if casting design is taken into account, the casting tolerances achievable in foundry, has the ability to maintain them with help of strict process control at their end. It is advisable that foundry uses sighting fixtures for such castings to monitor casting variations. सोनी साहेब खूप उशीर होतोय का?
कारण अजून मला वाटतं 30 एक तरी स्लाईड आहेत ना?
हो 15 मिनिटं तर लागतील.
हा 15 मिनिटं लागतील तर ठीक आहे, काही प्रॉब्लेम नाही.
I'll rush it fast to just mention the major points. Gating and venting system general consideration. I think this was discussed in detail by Janamurthy.
हो.
Method of gating calculations. I'll just briefly go through it, not formulas, just the concept. The metal is accumulated in the pouring basin at the top, and from there that becomes the height, and the potential energy of metal gets converted into kinetic energy. So this height energy gives rise to a velocity at the parting line, which should not exceed 80 millimeters, as I said. Difficult to achieve. Should be made to do that. So based on the quality of the metal, the composition of the metal, and the temperature, the fluidity factor is decided. The fluidity factor and the parting line velocity and the casting volume will give you the area of the ingot to fill the mold in the required pouring time. So first you calculate the arrive at the pouring time. My book on pattern design gives all those calculations and more theory on this. So first we decide the pouring time. What is the optimum pouring time for a given wall thickness of the casting, given weight of the casting, given composition of the metal, and this pouring time and the parting line velocity will decide the area of the ingot. That becomes the entry area of the gating system. Then there are other issues like ceramic filters, foam filters. As far as possible, see earlier there used to be high pressure, the pressurized system, non-pressurized system. But after we entered into the era of ceramic foam filters, instead of doing all this where the yield is little less, we can go for a neutral gating system where all areas can be same. The ingot area, the runner area, after taking, of course, taking into account the frictional losses, that is so they can be 10% or 20% higher. yield is improved. So maybe it can partially compensate the cost of ceramic filter. Ingates from base of runner, which is coke, which is in coke. With introduction of filter, this is no longer a constraint. These are the earlier guidelines. Filter should be selected from a list of filters in use. If the need is felt to introduce different filter, it should be discussed with foundry. For filter selection, refer the data provided by the filter supplier. In cylinder blocks, gates are normally provided at the bearing cap mounting faces. Drag flange gates are also desired as they reduce possibility of metal stream falling or cascading and entrapping air in the process. At times, gates are provided on cope side also. Cold metal related problems are observed, but in cope side ingates, metal runs over the pore and it can lead to core scab. Drag flange ingates with additional ingates in bearing cap, cope side only, should be the ideal solution to start with. Housing castings are generally gated at parting line on the wall opposite the print side. Positions of ingate should be such that metal stream does not directly hit the cores and smoothly rises in the cavity. If cylinder heads, position of ingate should be selected such that metal does not impinge on the water jacket core. Flow-ups are needed to drain away the cold metal on coke side. Flow-ups are provided in the direction opposite to the ingates and are connected to the highest point in the casting. They should always be designed such that they are easier to fettle and do not cause casting damage while breaking. Vents are of two types, gas vents and metal vents. All vents which are supposed to carry the core gases, generally during burning of core winders, are called gas vents. As a rule, they should open to the atmosphere. Height of mold from the parting line. These vents are fitted on core prints. Metal is not supposed to enter into this vent. Effectiveness of these vents depends on print clearances. Whenever shell cores are used, then gas venting becomes critical. Shell cores need to be drilled and to make a passage to the internal gases or the internal gases of the cores. These passages are then connected to the gas vents. Metal vents are which are meant to carry out the air inside the mold as the metal enters in the cavity. Metal vents need not be open to the all the metal vents need not be open to the atmosphere. Only two vents should be open up to the top of the mold height, which gives an indication to the pourer that the mold is filled up. Rest all vents should not exceed height to diameter ratio of 10. Feather vents can be provided, but after consultations with the foundry, pattern construction should be kept in mind under impact while molding. The vents are so very thin feathers and all may not stand the high pressure molding operations. Use of guide bars on pattern plate. This is a very, I would say, unique idea that we got. So whenever I used to attend a meeting in foundries, different foundries, always they used to discuss the mold breakage. And the mold breakage, to my surprise or to everybody's surprise, was more in drag than in cope. And cope, we find so many thin vent pins and runner bars, the down sprue and all that. In spite of that, the mold breakage, if you see the percentage, was less in cope. That gave us an idea that the vents, instead of breaking the molds, are helping the mold stripping arrangement to properly separate the mold and pattern. So similar vent bars we introduced in drag mold, which reduce the mold breakage in drag also. Modern trends in foundry, we are coming to the end, so let me very quickly go through it. Modern trends in foundry are all cores needed per mold in one shoot of the core box, so that product change or the setup change is much easier. All machines are employed for the same time. Candleless core making, horizontal versus vertically core shooters. We can discuss this separately on the core shooters, but horizontal core shooters provide a larger flexibility in making the cores, so it can make much more delicate cores than what the vertical core parted core shooter can. Modern tooling inspection techniques, key core concept. Many people must have seen it. One or two foundries are using this. We make the cores first, then put them in another core box and blow the sand in the key passage. Then it becomes a single core. These are the modern trends. Over the years, unavailability of trained manpower in foundry has forced process planners in foundry to rely more and more on automation. It reduces focus on man, but also makes repetitive actions error-free. At the outset, it looks very attractive alternative to all manpower-related worries in foundry, but in order to be successful, it needs very high level of process reliability. This needs extremely robust methoding as well as tool design and a very good and reliable quality of foundry materials such as sand, resins, paints, etc. Thinking of all the aspects of casting making well in advance before the tool is ordered is a must if one is going for a high level automation. Overall and thorough knowledge is the key of successful implementation of these high productivity, high cost solutions. Incorrect selection of raw material and incorrect process design can lead to underperformance of these high investment, high running cost machines. It can lead to disastrous situation leading to spiraling losses. Since all these efforts are directed to eliminate human element from the repetitive operations in foundry, the first thing which gets focus in this case is tooling. And then manual core box layout is extremely important. It has to take into account core assembly sequence. No matter what core is taken in core box manufacturing, there will be some core fin present in the parting line which is trimmed. In addition to core shooters, this operation is done by hand. In these new high productivity machines, the operation is generally integrated in the core box itself. It is called as trim tool. The cores are made and trimmed in the same core shooter. This trim tool can trim shearing action, pin at the plane parting line. If there are loose pieces or up-down parting lines, then it may have to be trimmed manually by introducing a manual interface in the automated setup. Like parting line pin, blow tips or blow candle. This all I am talking about the modern foundry setup where highly automated core shooters are installed. Like parting line pin, blow tips or blow candles also need to be cut from core and trimmed to the core profile. In advanced core shooters, which are generally horizontally parted because of their high productivity, the machine design allows making of the core without shooting candle. A simple way to achieve this is to bring the shooting point as close to the core surface and shoot. When the shooting is over, the blow plate having shooting nozzles retracts and then top ejector plate comes in. The top ejector plate, which is housed in gassing hood, serves as dual purpose. Ejector pins are set such that the loose sand is left, no loose sand is left. The loose sand left after the shooting nozzles retract is pressed to the required dimension by the tip of the ejector pin itself. Gassing and purging operations takes place in the position of ejector pins. While designing tooling for high pressure molding lines and high automation machines, it is strongly advised that 3D models of the machine elements coming in contact with the core box are prepared at their respective locations and they are checked with core box model from fouling, loading, unloading point of view. These core boxes are very big and stamping of core box weight on the core box and its parts is desired. Blow nozzles and ejector pin lengths also change as per their location on the core, and these lengths should be stamped on the base of the each element to avoid the confusion and so on, maintenance issues. Now let us talk about modern tooling inspection techniques. As CNC technology entered the manufacturing industry in late 90s, inspection by the old height gauge and vernier calipers became more and more tedious and less adequate. At the same time, coordinate measuring machines also became more and more available and affordable. Portable CMM such as FerroArm became available. These new inspection machines, along with software, can compare 3D model of the pattern, core box, or the casting and give the extent of deviations. Most of the portable CMMs can measure up to accuracy of 50 to 60 microns, which is sufficient for pattern equipment casting inspection. Portable CMMs can be touch type or scanner type. Touch type machines give point-to-point comparison between a CAD model and an actual tool. This is sufficient for tool inspection. Pattern or core box as a final product is a result of not only CNC machining, but there are many assembly parameters which are achieved using various conventional machines. Profile machining is generally done on CNC machines and there is less scope for error if the machine is in good condition and proper precautions are taken. Because of this, it becomes more important not only to check the profile but also the core box pattern and the mounting parameters required on molding line or on core shooters. In short, complete inspection using CMM for all tool parameters such as mounting holes, parallelity, tenon slots, etc. is a must. Scanner type machines are more desired for casting inspection. Generally, CMM software compares scan data and reference model and by the best fit method and gives the deviation report in a color-coded format. This can sometimes be misleading because software tends to distribute the error equally and gives the deviation report. However, in reality, casting gets machined with reference to the machine reference pads, throwing the error on the opposite side. In order to minimize this error, proper understanding of casting machining reference point is very important and should be told to CMM operator before going for CMM inspection. We discussed about the tooling material, so I'll not repeat that. Somebody asked about the core box cleaning last time. So let me spend a few minutes, 1 or 2 minutes on that. Best way, healthy and trouble-free life is a good hygienic standard and cleanliness for human as well as for foundry tool. This is true for foundry tooling also. After every run of the core box, it should be cleaned thoroughly and checked for basic parameters such as parting line gaps, right angles, wherever required. The equipment to do this is not really important, but the focus on this is important. A glass bead blasting machine is excellent tool to clean the core boxes. They can be cleaned carefully by hand also, of course. If the core box is always on the very rarely taken out, dry ice or solid CO2 is blasted on the core box. Interval or frequency can be decided based on the extent of resin buildup inside the core box. We'll spend some time on solidification analysis because even today the customers have started insisting on solidification analysis. Various CAD packages are available as for fluid flow as well as solidification analysis, which claim everything. Almost all packages today are capable of predicting actual metal flow patterns, peeling progress, and temperature distribution. They can also predict casting cooling and solidification pattern. Few of them can tell possibility of shrinkage defect occurring in the casting. But no package tells you how to eliminate a defect. What they can do is to analyze a particular foundry system and in some cases predict a defect. Foundryman then can change the gating or add chills or risers or analyze again and to see if the defect vanishes. It can be said to be a trial and error tool which predicts a defect without actually making a casting. But there are some hiccups. Foundry defects can come from various parameters such as mold, sand, core, metal, pouring practices, and methoding. Each of these are having sub and sub variables. Porosity in the casting can be gas, shrinkage, inclusion. One out of around 250 variables in foundry which affect casting quality, CAD packages can understand only 5 or 10. Other variables are either neglected or, if possible, CAD packages can be fine-tuned for the foundry under consideration. This could as well be a 6 month to 1 year exercise dedicated. In conclusion, we can say that CAD packages can compare product design A from product design B and predict which is the better design under a fixed set of foundry conditions. When it comes to a frozen product design, defect analysis using CAD packages is still not a perfected and time-tested approach. Some packages have now started claiming that they can even suggest solutions. It needs to be assessed that what percentage of this is a cell stock. These packages are more effective in HJN getting and risering. This is mainly because of two reasons. The castings are generally less complicated to model using a CAD software, model and analyze. And HGIN is more prone to shrinkage defect if not gated properly. This makes HGIN analysis job much easier and more desired compared to a typical gray and dropper head. First practical hurdle in the expertise is in this exercise is the availability of the CAD model of the casting with gating. Most of the foundries do not have the capability to do this. Many times they buy costly analysis packages but do not have supporting manpower to handle this software. Sometimes foundry can handle analysis package, but a small modification needed in the gating system is not possible. This type of approach does not work. Availability of trained manpower is a must in this if this is to succeed. With this, we come to the last slide, that is core box simulation and core box sand flow analysis. CAD analysis packages such as Arena Flow are used by many foundries abroad for core box design. But in Indian context, cost of these packages and availability of trained manpower to use this software is a major hurdle. This software can suggest, analyze effectiveness of blow tube positions as well as gas input and exhaust vent locations. It can be a very effective tool to avoid overventing of the core box. CAD models as visualization tools. A basic casting model is provided by the customer. It helps toolmaker as well as foundryman in many ways. It is an excellent tool for visualization. One can take sections at various locations, see the criticality of the casting and core sections, rotate and see the cores, which helps in deciding blow and ejection positions. Otherwise, difficult to visualize situations such as core-to-core fouling while placing in the mold can be avoided using CAD. Many times, product 2D drawings, particularly if they are very old, hand traced, etc., are insufficient to visualize and manufacture the cast part. But if the 3D models certified by the customer is available, such issues do not arise. With this, I come to the end of what I was discussing so far. Thank you very much.
Sir, there is one request from Mr. Mohit Kumar Sharma to please explain the candleless core making concept.
Candle is unwanted part of the core. So when you have a blow plate or blow nozzle resting at the top of the core box, the distance from core profile to the core box top comes as a candle. That is called as a candle. In cold or in a shell. If you have a larger stroke, downward stroke for your blow head or shoot head, then you provide a shooting point right on the surface of the core so that the shooting nozzle enters inside the core box. Many machines like Indian machines also give are capable of movement of top ejector plate to the extent of 120 130 millimeters. So to that extent, the blow tube can enter into the core box and blows the sand right at that point. So that produces the candleless core. This is generally true for horizontal core shooters, but modern core shooters for vertical parting also, like Loramendi, are having such designs.
Thank you, sir. I think there are no more questions, and I have already requested everybody that if they have any questions, they can send us on the mail.
Most of the questions will be answered if they go through this pattern design practical guidelines manual published by IIF NCTS.
That's okay. Thank you, sir. Now I request Mr. Shah Majur Adkar to give his concluding remarks and comments. Thank you.
Hello, good evening. Thanks a lot,
Good
Sanjeev.
evening. Good evening.
Yeah, it's really pleasure to listen to you. In fact, I have requested sorry that I may have to leave, but looking at the flow, I continued to listen to you, and it's a really pleasure. Uh, there is no point in repeating the same words what you have said. I mean, once you have listened to the Vedas, then you have to sum up in the Upanishads. And if you have to sum up into Upanishads, you need to have that kind of finesse to take out that. And still, I'm not qualified for that. So I will not repeat everything, but I will share a couple of experiences what I have in my career of a modeler. One is that the one comment I can say the very first and foremost came to my mind is that domain knowledge is inevitable. You need to have full involvement in the job what you are undertaking. You have to practice with dedication. Then only, as referred by Mr. Khanolkar, the sixth sense gets developed, and you can look at that drawing and you can understand what way you have to put. So domain knowledge is inevitable. You have to study hard. You have to practice hard. This is one thing. Secondly, the interaction with the customer. The most important point what I could gather from this is that the relationship with the customer and understanding of the customer and the customer requirement. Normally, the foundry, they get the quality plan controls or the quality plan, and the customer representative comes to check the quality plan whether it is observed or not. That is not enough. I can narrate a couple of examples in my career. What I say, I had been to Orleans factory in Zurich, Switzerland. And then naturally, as a foreman, I asked them the question that how could you get the casting? Are there any problems in procuring the casting or is that entire process? Because they were making the machine tools and the major input is the casting. So, but they said that they have a panel of their vendors, of the foundry vendors, and unless until their panel consisting of two from each side, unless until they clear, it doesn't go to the production. Right from the design stage, the designer is involved, uh, the user is involved. In that case, the user is the foundry who is going to produce the casting, and then the manufacturer of the pattern and the tool is involved. And all of them concurrently sit together, hours together. They spend the time, they understand the requirements of each other, and then they go for actual manufacturing, whether it is a tooling or a casting, and then they do that. So I certainly suggest that this culture has to be inculcated in our foundry so that we can have common a couple of people from both the sides. They always interact with each other, they understand the job, and they can clarify all the requirements of each other, and that will make you a smooth functioning company. I have my personal experience in that case with a very big car automobile manufacturer in Pune. I may not name it. They were interested in getting the castings. Urgently, they gave me the drawings. And then those castings had to be machined at somebody else. And as I said, there were problems from the reference points to making the rather reference points, and those are quite heavy castings. And those were the ERC. And then ultimately, then we had series of meetings before we started attempting to the productions with the machine shop, with the rather with the foundry, that is myself, I was involved, and from the Tata Motors, and ultimately the ERC guy from the Tata Motors who was involved in the designing of that. And once all those concepts are clear, all the requirements have been understood, and then we could able to beat the deadline or the target line to get produce the cast. Because as usual, as said earlier, the casting were required yesterday. So, but nevertheless, the efforts have paid, and as I said right at the first time, we could able to produce the casting, and customer is satisfied, and we were also satisfied with the efforts what have been put in there. So, in short, what we need to understand is that understand the requirements of each other. We must have a good dialogue, and there has to be a panel. If it is possible, we can develop a panel with the customer and a vendor, so that all these requirements are satisfied, and we can do the thing. And this culture, this requires a little bit cultural change and some might change in the mindset of the foundry executives. And of course, when I say the foundry and the vendor, I also include the toolmaker into that. So we have to see that nobody has got to play any hide and seek game in all this gamut. We have to be fair. We have to be transparent with each other. We have to be understanding with each other, and it will be powerfully. Okay, having said this about today's program, I think that this couple of hours is a very short time. As it is, you have been planning for a long time to have a couple of days program on these technologies. Because when I discussed with Mr. Khanolkar at early stage, we decided that what it should contain, that it should contain all these details where the audience should know what is there at the horizon. And very rightly, Mr. Khanolkar has told you what is there at the horizon. And horizon is a thing which is a dynamic. As you go one step ahead, horizon goes two steps longer. So we know what is there at the horizon. We know what we have to practice. We know what kind of culture we have to inculcate, and we know now how to proceed for the tool design and tool making. Well, I'm very thankful. I think the audience has been very happy with today's program, and I look forward that NCTS there should be arrangement for a workshop on such kind of that, and maybe if by God's grace, if the COVID is over, we can have a personal seminars or the program seminars per se what we look at the seminars, but the programs, the training programs on such subjects for a longer time, longer period, not a typical 45 minutes paper, but for a 2 week course or something like that. So real interactive should take place, real dialogue should take place, and understanding will be there because now the job is to pass this knowledge to the new generation and make the perfect foundation for coming era. So with this, I sincerely thank to Mr. Khanolkar, to our staff and directors who have helped coordinate, and the participants. I'm really happy participants have shown deep interest in this program and selected their questions for this. It shows the enthusiasm and interest in the technology. Well, with this, thank you very much. We'll meet again sometime after the COVID is over, personally, to elaborate much more on the subject. Thank you, sir.
Thank you. Thank you, everybody. Just for the information of all the present, our next two lectures will be on steel melting and sands and used for steel castings and coatings. Thank you. Thank you, everybody.